Hello, everyone, and welcome again to another Open Academy Alumni Meetup. My name is Marta. I'm the Open Academy e-learning and outreach coordinator, and as usual, I'll be today's host. We are letting everyone into the room. Get comfortable because we'll get started in a minute. So let's quickly go through some housekeeping while everyone is joining us. This session is going to be 1 hour and is being recorded as well as all the other meetups and masterclasses that we've done this year. It will be uploaded in a couple of days to the Alumni private page. Please mute your mic until it's time for Q&A at the end. If you have questions for our panelists, type them in the chat. But you can open the chat right now and introduce yourself and let us know where you're joining us from and what disease you represent. During the time for Q&A, you can speak and share your experience by clicking on the raise hand feature, and I'll give you the floor. And as we do in all the Open Academy sessions, we've created a short survey to assess your satisfaction and see how we can improve our future trainings. So once the Zoom closes, like the meeting finishes, a survey, like a super quick survey, will automatically open in a new browser tab. But if you cannot stay until the end, as usual, we'll put a link to the survey in the chat. There you go. Let me introduce you to today's speaker, although some of you may already know her. Annemieke is a professor at Leiden University, but also a longtime partner of the Open Academy. She's been on the Open Academy Program Committee and actively involved in our school since 2015. And today she's going to present the N-of-1 approach in clinical trials and the lessons learned through her experience. Before I hand over to Annemieke, I just have a couple of announcements. First one, you may have already seen that, but we want you to know that the applications for the Open Academy schools for next year are already open. Both schools will take place next June in Barcelona during the same week. And if some of you, I know that you've completed all our schools, maybe it's time to pass the torch and encourage other members of your organization or your network to apply. And if you've just done one of our schools, consider applying to complete your training in both medicines research and development and scientific innovation and translational research. Applications will close on October 27th, and the selected participants will be notified at the, I think, end of November. And 2 more meetups are planned between like now and end of October. You can register for the meetup that we are doing next week about the reform of the EU pharmaceutical legislation, where we have 2 speakers, 2 policy officers from the European Commission presenting the reform, and also our colleagues from the EURORDIS advocacy team presenting and answering all your questions. And in October, we've planned a meetup with Michaela Onali, who's a rare disease advocate and Black Belt awardee, where she'll share her experience on promoting research for her rare disease. That's all from our side. I'll hand it over to Annemieke. And yeah, I'll monitor the chat and talk to all of you later.
Okay, thank you very much, Marta. And I'll just share my screen as well. So, I'll hide this thing. My pointer, there we go. Okay, so welcome to this special webinar. And what I want to present today is on opportunities of antisense oligonucleotide therapies for very rare diseases. And I saw already in the chat that there are some people that were there last summer school, so this year, but also some people that were participating longer ago. So I'll start with a brief introduction into Duchenne, and some of that may overlap with what you heard last June if you were there, but I promise you the overlap will be minimal and the perspective will be different. So first of all, my disclosures, and I'll give an executive summary. My employer has patents on exon skipping. I have a potential, or I can get a potential share of royalties if there's income from these patents. And I do a lot of ad hoc consulting and advisory boards and speaker symposia, and the money that we receive for that all goes to LMC rather than me personally. And all these disclosures relate to the Duchenne work, so that's the first part of the talk, and not to anything else. So what we want to do today, or what I hope that we can achieve today, is that I can showcase that for the very rare diseases and the individualized treatment, traditional drug development is not, the route is not fit for purpose. So what we need to do is to build a new route and a new development path for this. But bear in mind, spoiler, we're building this. It's not there yet. So it's something that's in progress. There's ideas about this, but it's not yet done. So we're building it. What we do know is we need to collaborate internationally to make this work. We need to collaborate with all stakeholders, includes, of course, also patients. And as I said already, we're pioneering. So that means it's not yet ready, but it also means it's crucial that we learn from successes and failures. Because we're pioneering, we're going one way and then maybe discovering, well, this is a dead end. We need to share that information because otherwise everyone else goes into the dead end and that would just be a waste. There's also the risk that we'll discuss. But with normal drugs, you know the risk of the therapy, you know what the side effects can be, you know what the potential benefit will be, and you know what happens if you do not treat. However, this is a different type of thing because you have an experimental treatment, so you have the risk of not treating versus an uncertainty, which makes the discussion different. There's many unsolved issues as yet, as I mentioned, and well, we can discuss this at the end. How do we pay this? How do we sustain this? That is something that also we're still thinking of and discussing. So with that, let's move into the item or the topic. As I mentioned already, I will start again with Duchenne muscular dystrophy, which is a disease that I've been working on for, well, over 2 decades now. It's a severe disease. It occurs primarily in boys, and the disease is characterized by the progressive loss of function. So patients lose the ability to get up from the floor, they lose the ability to walk, they lose the ability to use their arms, they need assisted ventilation. And currently, most patients die between the 2nd and 4th decade of life. The disease is caused by a lack of a protein called dystrophin, and I like to use the carabiner as an example of what dystrophin does because it connects the inside of the muscle fiber to the outside of the muscle fiber, and in that way it provides stability to the muscle fiber during contraction. And it's similar to the carabiner because you don't need dystrophin to have muscle, you don't need dystrophin to use your muscle, you need it to prevent damage. And the carabiner, if you go rock climbing, you don't need the carabiner to go rock climbing, you need it when things go wrong. Now, what happens in Duchenne is that only the beginning of the protein is made, and of course then the connection to the outside of the fiber is not made, and there is no buffer function. So during contraction, there's damage. There's another disease called Becker muscular dystrophy, and you can see here the elastic middle is much shorter, but the 2 important domains at the beginning and the end of the protein, they are there. So these dystrophins are partially functional, and we know this because they're found in patients with another disease called Becker muscular dystrophy. And Duchenne patients, loss of ambulation before 12, assisted ventilation at age 20, usually die before the age of 30 or 40. Becker patients can have age of onset in childhood, but sometimes in midlife, and there's patients that have their first symptoms in their 40s or their 50s. So there's more variability, and also in general, the age of onset is later and the disease progression is slower. So I don't want to trivialize Becker. It's definitely a severe debilitating disease. But if you come from the Duchenne angle, it is less severe. So the approach that we've been working on at LUMC, but also other areas in the world, is called exon skipping. And the idea is to allow Duchenne patients, instead of making this type of protein that is not functional, to have them make this type of protein that is partially functional. So we use their own DNA, their own genetic information, to allow them to make these Becker-like proteins. And we do this with antisense oligonucleotides. So briefly something about antisense oligonucleotides, because they will feature in the rest of the talk. They're small pieces of modified DNA or RNA, and they're synthesized. So they're not biologicals or gene therapy. They are synthetic pieces of DNA or RNA. So they're produced. And what they do, they can bind to gene transcripts in a very specific way, what we call Watson-Crick base pairing, so that you can program them to recognize a specific piece in the gene transcript. And you can use that to reduce the production of a toxic protein, or, as we do in Duchenne and in most of the rest of the talk, we can use it to modulate the processing of the RNA transcript to restore the production of a missing protein. So this is what we'll talk about, but know that you can also use them to do other things. Just one example, this was a study done in 2006, where in 4 Duchenne patients, we did at LUMC a local injection with these ASOs in patients who needed exon 51 skipping. You see here a healthy control. This is a muscle biopsy stain for dystrophin, so green is dystrophin. See, the healthy individual has dystrophin. This is a reference of a Duchenne patient not treated. We don't see green because this patient doesn't produce dystrophin. And this is what happened after the treatment in the 4 patients. You can clearly see dystrophin is restored in each of these 4 individuals. Now, this was local injection. The challenge, of course, is that we have over 600 different skeletal muscles. They're all affected in Duchenne. So injecting each and every one of them locally, that's not the way to go. Bear in mind that these AONs, they don't last eternally. You will have to inject repeatedly because the AONs will be lost, the restored protein will be lost, there will be turnover. So this needs repeated treatment. So you might be able to talk someone into thousands or 1 million of local injections once, but not every week or every month. So we need to inject systemically. And then it's good to know that small things like AONs are filtered out by the kidney. And you don't need to understand this chemical modification, but we've used a chemical modification that prevents this filtering out by the kidney. And that then means that it will stay around much longer, because without this, you're making expensive urine. However, it stays around longer, but then it's taken up by the liver, which is the function of the liver, to take up drugs and things and break them down and clear them. So we know the uptake in skeletal muscle is poor. And this is something that we knew in 2005, 2006, and now, after 23 years of development, say starting at the 0 time point, where are we now? So there's 4 approved AONs. They're approved only in the US, 1 in Japan, not in Europe. And there's a reason for that. And that is that approval is based only on restoration of dystrophin at very, very minor amounts, less than 1%, generally speaking. After weekly intravenous infusions of very high doses, you get less than 1% of dystrophin restoration. And then the question is having these very low amounts of dystrophin, is that enough to slow down disease progression? And the answer is, we don't know. So the first of these 4 drugs was approved in 2016, so more than 7 years ago, and still we do not know whether it slows down disease progression. And there's confirmatory studies ongoing now to evaluate this. And what we can have a large discussion about this, but the bottom line is, why is it so inefficient? Because it's really difficult to deliver these AONs to skeletal muscle and heart. And so if we would solve this problem, things would work better, but we've been working on this problem for a long time, and so far, this is as good as it gets, very minimal amount of dystrophin. So when we were developing this for Duchenne, something that we learned is that we always thought delivery to brain and eye will be much more difficult because the brain is behind the blood-brain barrier. So if you inject something in the blood circulation, most things will not go into the brain. The brain is protected and has a special fortress that only allows certain things to go through and not others. And the AONs are in the not other category. They're not allowed to go through. So how do we then reach the brain or the eye? We can do that with local treatment. And local treatment for the eye means injection into the eye. For the brain means injection into the spinal cord fluid, so intrathecally. And of course, that is very invasive. If you would have to do that every week, that would not work. However, you don't have to do it every week. What we know now is the AONs, if you inject them in low doses locally, the cells from the central nervous system or the cells from the retina in the eye will take up the AONs very efficiently, and it will distribute throughout the central nervous system and throughout the retina. So that is very efficient, and then you get low exposure to the other tissue. So you don't get a high dose in the liver or the kidney, you get a very low dose in the liver and the kidney, and most of it is really sequestered in the eye or in the central nervous system. Now, that would not work if you would have to treat every week. Even every month would be challenging, but what we know is that maintenance doses for the eye are twice per year, and for the central nervous system are 3 to 4 times per year. So the dosing frequency can be much lower because once it's in this closed compartment of either the central nervous system or the eye, the turnover is much lower. So then, of course, does this work in diseases? Well, yes, in spinal muscular atrophy, it's been shown that this actually does work. And what I show here is the first placebo-controlled clinical trial that was done in spinal muscular atrophy type 1. That's the most severe form of spinal muscular atrophy, where normally within 2 years, patients either die or are on permanent ventilation. So it's a very severe disease. And the endpoint they used in this clinical trial was death or permanent ventilation. And what you see is that when patients got the controlled treatment, over 70% of patients was either on permanent ventilation or had died, while a much larger group of patients survived when they had the nusinersen treatment. These patients were treated when they already were symptomatic. We know now if you treat pre-symptomatically, the response is better, or even better, I would say. So what this shows is that if you want to target muscle, you need weekly intravenous injections at a very high dose. If you want to treat the central nervous system, you can do intrathecal delivery with very low doses, and you need to do this 3 times per year. And but we have a disease where we still don't know whether the treatment slows down disease progression, and we have a treatment where we know that if you do this, patients you prevent death in a significant number of patients. So there's a completely difference in how efficient these approaches are, and that is because you deliver much better if you inject locally. So the top part I just mentioned, but then when we realized this as academics, we said, well, there's one type of mutation. If we work on exon skipping, there's one type of mutation that is really the perfect candidate for exon skipping, and that's the cryptic splicing mutation. And I'll show you here what it is. So the gene contains the genetic code for proteins, and this genetic code is dispersed over exons. So before this genetic code can be translated into proteins, these exons need to be linked together, and then you have translation. Now, a cryptic splicing mutation is a mutation that causes part of the non-coding part of the gene. So you can see here there shouldn't be an exon here, because here, look, it's empty. But now due to a mutation, suddenly this part is recognized as an exon, even though it doesn't contain genetic code. So it's included into the transcript, and now it's translated, but it doesn't contain genetic code. So this stops protein translation or production. If you would block this, and you can do this with AONs or ASOs, same thing, then what you end up is the normal transcript So it's not like in Duchenne, where instead of partially functional protein, you go to, or from non-functional, you go to partially functional protein. Here you go from having no protein to having a completely normal protein. So that is very, the eligibility is really high, and it has high potential. However, these cryptic splicing mutations are very, very rare. So that poses a challenge. And in 2015, 2016, what Tim Yu did in Boston, or 2016, I should say, he discovered a cryptic splicing mutation in a patient with Batten disease caused by mutations in CLN7. So he discovered she has this cryptic splicing mutation. Nusinersen had just been approved by the FDA. He thought, well, this is a brain disease, lots of epileptic seizures, progressive neurodegeneration. This is a brain disease. This is a cryptic splicing mutation. In theory, AON should work for this patient. However, she has a unique mutation. So there won't be a company interested in it, but I'm going to see if I can develop this myself. So he designed AONs, tested them in fibroblasts from the patient, had discussion with the FDA for studies on toxicity, submitted an investigational new drug application, or an IND, and then within a year of finding the cryptic splicing mutation, he treated the patient for the first time. Now, the mother of this patient, and the patient was called Mila, and that's why the drug is called Milasen. The mother of Mila kept an epilepsy diary. So she would per day see how many epileptic seizures does my daughter have, how long do they last, are they very short or are they long? You see here before the treatment that on average, Mila had more than 20 epileptic seizures, and they generally lasted more than a minute. Now, when the treatment started, and you can see here dose escalation until a certain dose and then further escalation, you can see that the number of seizures goes down, and you can also see that the duration goes down. So there was definitely a treatment effect here. Was this a cure? No, it wasn't a cure, because Mila was blind when they started the treatment, and she stayed blind due to the treatment. She already lost the ability to speak. She didn't regain that. And sadly, she died due to the already existing neurodegeneration. She died in 2021. However, the family said the fact that she had less seizures for them was a huge improvement in the quality of life. And of course, they also said if we had the treatment earlier, well, it might have worked better. But of course, that's speculation in hindsight. But there clearly was a treatment effect, and the family said, for us, this has improved quality of life, and they felt that also for their daughter, it improved quality of life. So we were inspired by this, and not just us. I'm of course giving my perspective because that's one that I know, but no, there's other initiatives like this out there. To do this, to develop AON therapies for patients with very rare mutations. We want to do local treatment, eye and CNS, because we know that we can reach those tissues. And we're trying to set it up within an academic setting, and we're collaborating. So it's not just the Leiden University Medical Center where I work, but also Nijmegen and Rotterdam medical centers. Nijmegen works on eye, Rotterdam on neurodevelopmental diseases, and LUMC on neurodegenerative diseases. But we collaborate and share knowledge. So for whom and how? So the mutations must be very rare. We're not going to compete with companies. We want to offer something where we say there is a unique opportunity for these patients, but no one else is going to develop it. We focus on exon skipping because we have an expertise there. And of course, then exon skipping must restore a protein function. Target tissue, brain or eye, I mentioned already. And it's really important that the patients have to have expected benefit from the treatment. So if they're fully blind, the treatment is not going to undo that. However, if they're legally blind but can still see, well, remaining that last bit of vision is going to be important. So that would be clinical benefit. Same thing if patients are born with pathology because things go wrong in utero, then the postnatal treatment is not going to undo these anomalies. So that would not be an eligible treatment because we wouldn't expect benefit. But of course, if there's progressive diseases, then slowing down that progression or even stopping it would be benefit. Obviously, patients must be willing to undergo this treatment because it's experimental treatment, it's N-of-1. We will never get enough information to show that we can register the drug. It's an experimental treatment, so patients and families need to understand the risks of not knowing whether it's effective and not knowing whether it's safe. So we launched this on Rare Disease Day 2020, which we thought was a really nice day to start. But then 2 weeks later, the lab was closed because there was this pandemic thing. What we could do was having Zoom meetings, and we had a lot of Zoom meetings with the Dutch regulators, with the EMA, with the Dutch payer, so that's ZIN, with the patient organization, with our hospital pharmacies, with the Minister of Health, and many, many others. And what we learned from this is that in the US, you need FDA approval even if you want to treat a single patient. In Europe, you don't have to, because there's the named patient setting. A clinician can request for experimental treatment of a single patient if they think that there will be benefit and that it is safe. So you don't need regulatory approval. In most countries, you need approval of your local hospital ethic review board. The fact that we don't need regulatory approval doesn't mean that we're skipping them entirely. They're very willing to advise us, and we're very grateful for that. So we communicate with them for advice, but we don't need their permission. Because it's a named patient setting, we do not have to do it GMP compliant and GLP compliant. So the medical grades and the way you do toxicity studies, normally there's very strict regulations, and you have certified labs that can do this. Now, we're going to do it with the same rigor, but if you want to do it in the certified centers, it takes a lot of money to keep them certified. So doing that is very expensive, but also there's waiting lists. So if you want to get your compound from a GMP compliant group, there's often a waiting list of 9 to 12 months. Same for safety studies. Well, we don't have this amount of time because we have one patient for whom we developed this. And then if we wait for 9 months and then for 12 months, by the time that we're ready to treat the patient might not be there or have lost functions that we want to keep. So we want to be more flexible, we want to be quicker, but of course we want to ensure as much as possible that there's efficacy and safety. And one other important thing, what we cannot do here is measure the treatment in a placebo-controlled trial. We have just one patient. So what we can measure is before the treatment and after the treatment. So what's really important is to have discussions with the patient, with the family, what is a likely function or a likely benefit to be expected from the treatment, how can we measure this, then to start measuring the trajectory before the treatment, while the treatment is being developed in cell models, and then to measure after treatment, what do we see. So this graphic, and thanks to Annelien for facilitating that it was produced. So this really outlines on the top the traditional drug development path, where it takes years and years and years to develop it. And sadly, this means that by the time that the drug is ready to be in a clinical trial, patients who needed it at the beginning, they may already have lost functions, they may already have died, but there will be other patients. And as sad as it is, this is how this drug development works. If you have just one individual in which to treat, well, we can't do it like this, because by the time we say, look, we have now something to test, the patient might no longer be there, but also we cannot test it in larger groups where we compare treatment versus non-treatment, because we simply have just one individual. And I mentioned already, we need to start collecting natural history and then assess a treatment effect afterwards. So what are we doing now? We're looking within the DCRT, we're looking into patients with rare diseases. We have 3 patients for which we're trying to develop this into a clinical treatment. At LUMC, we're in an earlier stage, so we have identified a candidate patient, and we're currently testing in the cells whether the treatment works. And it seems to work, but of course you need to do more work to see whether it robustly works and whether it's optimized. In Nijmegen, they're further advanced. So for 2 patients with Stargardt disease, so a genetic eye disease, they have a lead candidate identified and are now preparing for treatment. So manufacturing it in an almost GMP grade like manner, and also to see, well, how can we start the clinical implementation. And I will skip this.
Anamika, we just have a couple of questions in the chat. So we have one from Juliana that says, can you explain the in utero mutations more? Isn't the DNA the same as in utero?
Yeah. So
and also about line 1 insertions are also cryptic exons. It seems the same mechanism.
Yeah. So starting with the in utero mutation. So the problem is, so mutations like this, they occur in the first cell. So the fertilized cell, the mutation is present there. So the mutation will be present in all the cells of the body. What matters is what happens when you have the mutation. And in some diseases, what happens is that due to the mutations, things will go wrong in utero. And then if you treat patients postnatally, well, you can't undo that, for instance, part of the brains were never formed. You won't be able to undo that because, well, you're too late. For other diseases, they will occur later. So the example of Mila, she was developing normally, even though she missed the protein, she was developing normally until she was 3 years old, and then started to have symptoms and to progressively decline. So that would be a disease where we would be able to intervene and hopefully slow down disease progression. So it's not so much that where is the mutation, when does the mutation start? The mutation starts in the one cell system already. It's when does it become apparent? And that depends on where the gene and the protein that the gene codes for, when that has a role. If it has a role in embryonic development, well, we won't be able to undo things postnatally. If it has a role in maintenance of brain of toddlers or later on, then it is something that we can correct. Then about the line 1 insertion, so that's the type of mutation that Mila had, was a line 1 insertion. So that's how a cryptic splicing mutation can arise, but there's also other ways that they can arise. So that's why I didn't specifically mention it. There's different ways how cryptic splicing can start happening, and we're targeting all of them.
Great, thank you. There are a few more questions, but maybe we can answer them at the end if that's all right.
Yeah, okay for me. So I mentioned already in the learning points that what's crucial is to not do this in isolation. So we have the Dutch Center for RNA Therapeutics, but we're also working European-wide with a network called One Mutation, One Medicine. And that's because in Europe, there's this named patient setting, but how it works, that differs per country. So that's something that we can align, coordinate. There's processes that will apply to everyone. There's processes that will be country specific, and we coordinate that from the One Mutation, One Medicine initiative. Then we're also aligned globally. So you can see the Netherlands here, but you can see that there's people from different countries. There's even Japan. This is coordinated from Boston. So the mother of Mila, Julia, and the first clinician who injected Mila, Tim Yu, they have said, we need to have a collaborative effort, the N-of-1 collaborative, to really align these things worldwide. And the way this works is that we see that there's things that need to be done, either nationally, continentally, or globally, and we see how we can help. So we provide pieces of the puzzle, other groups and people provide pieces of the puzzle, and then we really learn from each other. There's also a task force from IRDIRC, the International Rare Disease Research Consortium, and that is not just for AONs, but for all N-of-1 treatments, because there's also things that apply not just to AONs, but to everyone. And that's really another global group that tries to see, so what are the challenges? What do you need to have in place to do N-of-1 development? And we will produce some statement papers. And also here, again, we see that there's pieces of the puzzle that that we all will need. There's pieces of the puzzle that you only need if you work on AONs or only need if you work on gene therapy. And there's pieces of the puzzle that you only need if you work in Europe or in Japan or in Africa. So we really try to provide as many pieces of the puzzles as we can, and also discuss which puzzle pieces are not there yet. So some examples of things that we're trying to produce locally and European-wide. The first is a gene list. So this question about the in utero that we just had. So which genes, if they're not working, cause problems that we won't be able to correct? And which genes, if they're not working, cause problems that we might be able to correct because it leads to a brain or an eye disease that is progressive. So we have a person, a clinician, who is manually going through all the genes and see, well, would this be an eligible gene, yes or no, based on specific criteria? And we're sharing this gene list on our website. So that's useful for us as DCRT, but useful for the global community as well. So what we also know is that seeing whether a mutation is eligible is really difficult. So even if you know what the gene is on this list, is this specific mutation eligible, yes or no? Well, as you can see, there's a lot of these yes, no, yes, no, yes, no question in a decision tree. And every one of these, to answer each of these questions, you need to do software analysis. It takes time. And these are things that can be automated. So this is something that we're now setting up with Exon Check, is what the software is currently called. I think it will get a new fancier name. But we're trying to automate this. And again, this would not be something that we're only developing for the DCRT. This would be shared widely. And it's something that what we hope is that can also be implemented in diagnostic screening tools. So when a mutation is identified, that it's flagged to the treating clinician, look, this is something where N-of-1 treatment might be an option. Because then, of course, we can catch these patients earlier. And it will be up to the family and the patients whether they want the treatment or not, but at least that way they will be identified better than they are now. I mentioned the One Mutation, One Medicine already. So this is a collaboration of LUMC with the Tübingen University and Heidelberg University. Holm Grosner, you might know, so he has presented at Open Academy before. He is coordinating a network for rare neurological diseases and doing a lot in diagnosis. And Matthijs and Rebecca are adult neurologists that have thought a lot about outcome measures and implementing this type of approach. And Willeke and I are people that have a lot of experience with seeing whether mutations are eligible for exon skipping or not. So we've been having a lot of meetings as well, and I think it's important to bear in mind, so whether someone is eligible is determined by a lot of factors. So the mutation must be eligible, it must be exon skippable, and then lead to a partially functional protein. Disease needs to be eligible, and this is again the question, where do things start going wrong? Does it all happen in utero or later? But also the patient needs to be eligible. And I'll just give you some example, because the challenge is that often 2 of the 3 criteria are met and not all 3. And then, of course, patient is not eligible. And some examples of why patients are not eligible, we've had a patient with severe scoliosis, so he couldn't have intrathecal delivery. Well, then, of course, it's not going to happen. We had a patient who at first thought she wanted this, but then changed her mind. She said, well, intrathecal delivery, too much burden. Currently, my disease is relatively stable. I don't want this. And of course, that's her prerogative. We had a patient who was very afraid of needles and said, I don't want this. So there's different sorts why this cannot happen. But there's a lot of things that have to be tested. And what we thought is, well, what we don't want is that a few people decide whether someone is eligible or not, because that doesn't feel very ethical and justified. So what we want to formalize this process. That's something that we've done with N-of-1 and N-of-1. So we look first, is the mutation eligible? And if in that case, well, for this disease, how would we develop it? What would be outcome measures in cell cultures? What would be outcome measures in clinical trials. And then when we think, well, it all fits, then we have a treatment board meeting, which is a larger meeting with not just experts in the disease and the protein, but also experts, patient representatives, external experts, people who can have an objective look and see, does it make sense what these people say? Is it scientifically justified? Is it ethically justified? Etc. So a group makes this decision of whether a patient is eligible and not just a single individual. So I mentioned already we have had discussions with EMA about this, and we're very grateful for their help and input. And this has resulted in a publication as well. I think the bottom line I mentioned already, in Europe we can be more flexible, and that's also what the EMA has told us. But they also said it's really important to only do this if you can measure an effect within a given time frame of 2 to 4 years. Because you have the burden of the disease, and if it needs 10 years with frequent intrathecal injections and, well, the stress of being uncertain whether the therapies work, they said that is not justified. And another thing that they said that we fully agree with is, it's not that you say, okay, we start a treatment and then you start a treatment and never look back. No, you need to regularly check with the families, with the patients. Okay, we said that we were going to do this. We said that this is a burden that's unacceptable. This is acceptable burden. This is the benefit I expect. And every time check, are these criteria still met? And also, do we want to change it? Because maybe a patient said, well, that burden I really don't want. But then when it happens, say, well, it's not as bad as I thought. Or I thought I could cope with this, but now that it happens, I realize that I cannot. So it needs to be communication with the clinical team and the family to check during the treatment whether all these things are still met. So then finally, I have 2 examples of global communication. And the first one is a very nice and positive one, because this was in early 2021, pandemic, so we couldn't travel. But I had met you before and started working with him in the N-of-1 collaborative, and I met Matthijs online, and we started working in the 1M1M network. And then Matthijs said, well, I want to start developing this for patients with ataxia telangiectasia, which is a progressive neurodegenerative disease in children. And he had a patient where he said, this is a cryptic splicing mutation, an ASO should restore this. Will you help develop this with me, because you have the exon skipping expertise? And I said, well, I'm happy to help you, but I know that Tim Yu is also working on ataxia telangiectasia. So let's first check, because in theory, it's N-of-1, it's individual cases, but let's make sure that the patients, the 2 patients that he's treating, that one of them doesn't have the same mutation as your patient had. And it turned out that actually his patient, you can see a picture here, had the same mutation as one of the patients that Tim Yu was already treating. So an AON was there already. Now then we thought, okay, easy peasy, Tim ships the AON to Germany and Matthijs starts treating this patient. That's turned out not to be possible, because the AON had been filed with the FDA, so it was listed and it couldn't be easily transferred. So instead, the patient and his mother had to go to Boston. The treatment had to start there, while the father and the other siblings were staying in Germany. And then after 9 months, the treatment was started, and then the patient with the AONs could travel back to Germany, and currently the treatment continues in Germany. So that is, the end is nice, but of course it does show, again, there's these rules and regulations that probably make sense for larger groups of patients, but I think we all agree that in the future, the AON should travel rather than the patient and the families. But at least this boy is being treated, and he's doing really well. Then the final example is less nice, but it is important to mention as well. And this is a case from Tim Yu, where there was a patient with a very rare epilepsy syndrome, hundreds of seizures per day. And this is not the exon skipping approach, but the other approach where you try to reduce the production of a toxic protein. So Tim developed an AON for a child called Valeria. So the drug became called Valeriacen, and started treating the patient with it. And the number of seizures went down a lot, and almost to zero. So then there was another patient with the same disease where he said, well, this should be eligible to me as well, or the family said that, and he started treating that second patient. Then a few months and years after treatment, in the patient who started treating first, they saw hydrocephalus, so increased pressure within the brain, and that caused pathology. By that time, they discovered it. The patient was already in quite a severe state, and they could have built in a shunt, so a tube to reduce the brain pressure, but the family decided they did not want this. So they stopped the treatment, and sadly, this patient died. The other patient, where they noticed earlier, because he started treatment later, they did treat her with the shunt, and then the hydrocephalus went away, but the seizures gradually came back. And currently, there's the situations where the families say, we prefer to have the risk of hydrocephalus returning and then to treat it with a shunt. We prefer that over the number of seizures that we're currently treating. And this really shows that for these very rare severe diseases, yeah, you're willing to accept more risks because you know, like this also the risk of non-treatment is also really large. And I think so. Why did this AON lead to this hydrocephalus toxicity? It was properly screened, so they did all the safety studies that they should have done, and it came out clean. But when you do your toxicity studies, you test this in healthy brains from rats and monkeys, and that's not the same as a pathological brain of a patient. So the going hypothesis is that probably the combination of the pathology of the patient with the AON treatment resulted in the side effect. But the good thing is that Tim immediately shared, when this happened, immediately shared it, and also shares this AON with everyone to try and study, so what went wrong, and can we find something where we can predict in the future that these AONs will behave the same way to then not move them forward into the clinical trials. So also highlighting this case because it's not all going to be success stories. It's new thing. We have to develop this, and that will take time. So in summary, I hope I have convinced you that the AONs offer unique opportunities for mutation-specific treatment. N-of-1 AON treatment is feasible for brain diseases, likely eye diseases as well, but that's still in development. And the scientific context is different because it's mutation specific. Every time you have a mutation, you have a different disease. And even if you have the same disease and the same mutation, it will be different patients and they will be in a different stage. But there's common processes, and that's something that nationally, European, and global-wide, we're trying to align and learn from each other as much as possible. And all these efforts, it's not a group of researchers or a group of clinicians. We're really doing this also with patient advocates and patient communities. So this is the website of the DCRT RNA therapy.nl. And these are the people from the DCRT in Leiden, Nijmegen, and Rotterdam. And I really just want to highlight this list because it shows, again, it's not just researchers. We need a big group, we need a village and to make this work and to implement this into patients. And with that, I thank you for your attention, and I will stop sharing so I can see faces, and happy to take more questions if they are there.
There are quite a few questions. I think we can start from the beginning. Christina asked, are patients with comorbidities of 2 or more diseases, which in combination are ultra rare and sometimes are in contrary with the treatment to each other, are possible persons to have studies on?
Yeah, so I think, so the answer is, it depends. So what we will do with this treatment is treat sometimes all the symptoms, but sometimes part of the symptoms of a disease. So the patients, the families need to be, they need to be clear, like, this is what will be treated and this is what won't be treated. And then if they say, well, if these symptoms are reduced, for me, that would be benefit. then it's a go. But if they say, yeah, but actually what bothers me most is pain, and that's now not treated, then probably they wouldn't add the burden of the local treatment. We've had one example also where we had to say no due to a comorbidity. And so that comorbidity was not related to the rare disease that the patient had, but it just was something else. But it added a lot of burden to the patient. And then we said, well, the burden of having this is already so high that if we now start to pester the child with repeated intrathecal injections where we don't even know whether they will be therapeutic, that's just adding too much burden to already a child that has an extremely high burden. So really it depends, but it also depends on the perspective of the patients and the families.
I think that Sophia has raised her hand.
I
Would you
have
like to ask a question?
That was an amazing talk, really interesting. I thought it was easier to ask than type everything out. We're CACNA1C. What's your thoughts on CACNA1C, given it's expressed in 7 different tissues that we know of at the moment?
Yeah, so I think this is again the same thing. So it depends. So it's expressed in different tissues. The tissues that we will be able to treat locally are brain and eye. So the tissues where we expect therapeutic effects are brain and eye. And if patients then say, well, we suffer most from the symptoms that are caused by not having this expression or having wrong expression in brain and eye, yes, then the treatment would be justified. But if they say, well, but really the liver problems are the major problem, we won't be able to address those. So it will really depend, and it probably will depend on, because in some patients the neurological symptoms may be more, and in others other symptoms may be more. So it's really, even if you have multiple patients with the same mutation, and you could say, well, this is N-of-7, every patient will be a different case because they will all have these different things. Well, what is the most dominant symptoms? And even sometimes the most dominant symptoms isn't bothering some patients as much as it is others. So it really is a case-by-case situation. Yeah.
Thank you.
Okay, we can move to the next question. Jill asked, have there been any unexpected outcomes?
Yeah, so I think the case that I showed, the valeriacin, that was of course an unexpected and also really unwanted outcome. So I think that is one. I also think the Milacin, the way that her epileptic seizures went down so quickly, that was, I mean, it was great, but we didn't expect that it would be that apparent. So there have been unexpected outcomes, and in the future there will be more unexpected outcomes. And I think the most important thing is to share those and to keep sharing those, because then we can learn. Because, well, if it's unexpected once, then it can be expected the next time, unless people know that it happened.
Okay, and then Cynthia asked, are those N-of-1 treatments also aimed to restore single variant mutation, maybe the most recurrent, that can affect many patients with the same gene mutation, but also same variant, or only unique patients?
Yeah, so I think I understand the gist. So I think first of all, we started thinking very rigidly N-of-1, so only unique. But we've seen already that N-of-1, well, if it then turns out that there's a separate patient in Germany with the same mutation, are you then going to say, well, now it's no longer N-of-1, so we stop the treatment? No, of course not. I think the way Tim Yu says it is, let's call it N-of-1 at a time, because one at a time you see, would this patient be eligible? Even if they have the same mutation, they might not be eligible for reasons that we discussed earlier. So I think that is one thing. There may also be cases where you start in a single patient and then indeed realize, well, actually, if this works, it may also work for patients, even with a separate disease where the gene involved is the same, or for a larger group. And that is something that has happened with the JC Fusen compound. So that's an AON for a specific type of ALS called by FAS mutations. A company had been developing it and said, it's too rare, we're going to stop this development. We'll never be able to do clinical trials. And then an ALS patient approached the clinician and an academic group and said, I want you to develop something for my disease. And really quite a convincing story. So they said, okay, we're going to do this, and then discovered, but there's already something on the shelf. Ionis, the company developing the compound, said, here you can have it, treat the patient and see what happens. Well, by the time they started the treatment, patient was already in rapid decline. You could see that it slowed down ALS, but it was already in end stage, so they couldn't avoid things. Then, of course, people heard that and said, well, I have the same type of ALS, please treat me, I'm in an earlier stage. And they treated a few patients, and then the response seemed to be bigger. And then people, of course, started pushing, and now they're doing a clinical trial. So it started out as N-of-1 and now ended up being a clinical trial. So that can happen as well. And I think, again, we're not in the N-of-1 space to become rich. And if it's something that turns out to have a larger impact, we're happy to give it to companies to then develop it for more patients. I think that's all fine as long as the patients are benefiting from it.
Mm-hmm. Okay, moving to Paula's question. She asked a two-part question. What about when the mutations are in the mitochondrial DNA? Because she's representing Leber's hereditary optic neuropathy, which is a mitochondrial eye disease which affects the ganglion cells in the optic nerve. It is considered a brain disease. Would patients be eligible for this treatment?
So I think so. If it's in the mitochondrial DNA, the answer is that I don't know whether it would work or not. So I mean, we would have to study that. I think it is more difficult for sure if it's in the mitochondrial DNA. And then I also know that some of them say there's nuclear genes that produce proteins that then go into the mitochondria. Those, yes, but purely mitochondrial DNA, I think it would not be possible, but I'm not sure, and it might be possible in the future. But it's definitely less straightforward.
Got it. And then one last question from Yulana. Do patients need to pay for 1M1M treatments?
So that's a very good question, of course. So for now, in Europe, these initiatives are all funded by the local institutes, by EU grants, by national grants, and we're not asking patients to pay for anything. What we hope to do is that when this is developed, that the health insurance will cover it, and that we say, look, this is what it cost us to develop it. We will need some markup because not everything will succeed, so some will fail. But this is what it will cost. We'll add 20-25%, and then that is what the drug will cost. And then these are the maintenance costs because patients will need to go to hospital, need to be checked. So that is, say, what we hope will happen, and we already started having these discussions with the payers. For now, they say, first show us that you can do this. And that's, of course, what we're doing now. If you look at the example of the German patient, the AON was given for free by Boston Children's Hospital. And the German hospital is absorbing the cost. So they pay for the cost of having the clinician treat the patient, doing all the observations, etc. So they absorb that. And I think also here it's interesting to see a difference between the European and the US situation. In Europe, if a patient would have a side effect, then again, they would go to hospital and the insurance would cover this. I mean, we have our social healthcare system. In the US, if the patients have side effects, like the drugs are usually, or the AONs are paid, and or they do crowdfunding or they find other ways to pay for it. So they don't, I mean, this is covered. If they would have a side effect and end up in hospital, they would have to pay for that themselves. So that makes the situation in the US a lot more difficult than in Europe. And I see people, I heard, when I was appalled when I learned about it as well. So the risks that people take in the US are much, much larger, also because healthcare is much more expensive there. So that's definitely something, and it's also something that as this EARDER task force, we want to discuss, like, how can we make this sustainable, and how can we work with the different systems? How can we make it sustainable in Europe, but also in North America, South America, etc.
I think we have time for one more question. If anyone wants to raise their hand or post something on the chat. If there are no further questions for Annemieke, we'll just wrap up here and finish the call. As always, I want to thank Annemieke for a super interesting presentation, lots of questions, very high level questions, if I must say, from all the participants. So thank you everyone for spending some time with us today, and I hope you can join us also next week for the next Open Academy Alumni Meetup. Have a great weekend. There's one more question. Sorry, Christina, what would be the way to bring patients together with Annemieke?
You don't have to have very advanced Google skills to get my email. And you can also email dcrt@lumc.nl. You can also email that. Yeah. Perfect. So feel free to email.
Sounds good. We can put Annemiike's email address in the alumni page, and you can reach out to her. Okay, thank you everyone. Have a great weekend. See you all soon.